Hey, welcome to iLectures, and this time we're going to do a problem involving Newton's second law with an inclined plane, and this time the inclined plane has friction. There's friction between the object and the inclined plane. And so let's go ahead and read the problem and go ahead and solve it. It says here that a 50 kilogram mass is placed on an incline that makes an angle of 30 degrees with respect to the horizontal. The coefficient of friction between the mass and the incline is 0.2. Find the acceleration. All right, so again, we start out by making a drawing, a picture of what's physically happening. So here we go. We have a mass on an inclined plane. We say that the mass is equal to 50 kilograms. The angle that the inclined plane makes with the horizontal, theta, is equal to 30 degrees. And we can also mention that mu stands for the coefficient of friction, is equal to 0.2. And we're supposed to find the acceleration. A is equal to question mark. That's what we're looking for. All right, again, to solve a problem like this, we realize we're going to use Newton's second law, F equals ma, which means that A is equal to F divided by m if we divide both sides of the equation by m. And again, to find the acceleration of anything, we always want to deal with the net force. There will be a lot of forces acting on the mass, but there's only a net force that actually causes acceleration. So we can actually call that the net force that we're looking for. All right, to find the net force, we're going to draw all the force vectors, starting out with the force due to gravity, pushing down or pulling down on the mass, which is equal to mg. We then draw the vertical and not the vertical, but the perpendicular and horizontal components of that force. So here is the mg cosine theta. And this would then be the mg sine theta. Notice that this angle right here, theta, is the same angle as this angle right here. Now, once we draw the components of the weight is no longer there. We've now replaced the weight by those two components. Now, since the mass is pushing down on the plane, that means that the plane is pushing back against the mass. Newton's third law tells us that there's an equal and opposite force. Whenever there's an action, there's equal and opposite reaction. So this is the normal force, and the normal force must be equal in magnitude to the mg cosine theta. And of course, now you can see that those two forces cancel each other out. In addition to that, there is friction. And the friction, by definition, is caused by the normal force. There's a force between the object here, or you could also think about it as the weight of the object pushing down the plane. There's friction between the plane and the object. And the friction always is directed, or the friction force, I should say, is directed in the opposite direction of where the object will move without the friction. So imagining there's no friction, the object will slide down the incline. So we know there's going to be a friction force pushing back in the opposite direction, trying to retard the motion or retard the acceleration. And the friction force, by definition, is equal to the normal force times the coefficient of friction mu. And since we know that the normal force is mg cosine theta, this can be written as mg cosine theta times mu. So now you can look at this, that these two forces cancel each other out, and now only these two forces are acting on the object, mg sine of theta, causing it to be accelerated down the incline, but there's an opposing force, the friction force, pushing upward. Now, obviously, if this friction force is as large as the mg sine theta, then the object will not move at all, it will stay there. But if mg sine theta is bigger than the friction force, the object will then slide down the incline. So, since this is aiding the acceleration and this is opposing the acceleration, the net force then becomes mg sine theta, which is the force that aids the acceleration or causes the acceleration to happen, minus the friction force, which is the mg cosine theta times mu. This is the friction force trying to keep the object from accelerating. Of course, I'm assuming that the acceleration will be in this direction. And now I divide that by the total mass. If I now go ahead and simplify that algebraically, I can see that I can factor out an mg, so this becomes mg times the sine of theta minus the cosine of theta times mu, all divided by m, the mass. then the masses cancel out, and finally can say that the acceleration is equal to g, the acceleration due to gravity, times the sine of theta minus the cosine of theta times mu. And then I go ahead and plug in what these things are equal to. So this is equal to 9.8 meters per second squared, the acceleration due to gravity, times the sine of theta. Now the sine of 30 degrees, that's equal to 1/2, minus the cosine of theta. Now the cosine of 30 degrees is, you can look it up on the calculator, 0.866, so 0.866 times mu, which is 0.2. Now we go ahead and work that out. Now, of course, I'm going to need a calculator for that, which I have handy right here in my back pocket. So we take 1/2, that's 0.5, minus the product of the cosine of 30 degrees times 0.2. Okay, so I can put the intermediate result. Wow, I dropped my pen here. Okay, so this is equal to 9.8 meters per second square, and you can check this out with me. You should get, for that, 0.3268, rounded off to 4 significant figures. Then we multiply that times 9.8, and the result would be 3.2 meters per second square acceleration. There we go. Now, why did I leave it with just 2 significant figures? Because I used the number 9.8 that only had 2 significant figures, so your answer should also only have 2 significant figures. So the acceleration in this case is 3.2 meters per second square. All right, so we'll do a few more of these types of problems for you to get a good feeling of how to work with F equals ma.